So fluid mechanics, this is mostly fluid statics though, right? A vertical U-tube of uniform cross section contains mercury in both arms. Let's say this is the original level of mercury, OO prime. This is the original level of mercury. A glycerine column of length 10 centimeters is introduced in one of the arms. Let's say on the left arm, glycerine column is introduced. So this level will get depressed and this level will rise by the same amount, right? So the final level is, this is glycerin of length 10 centimeters, glycerine from A to F, and if this goes down by a certain amount, this rises by the same amount. So this is the final level of mercury in this tube, this is the final level of mercury in this tube. Oil of density 0.8 grams per cc is poured in the other arm till such time that the upper surface of oil and glycerine are at the same level. This is the upper level of oil and glycerine common. So this is oil. You want to find the length of the oil column. You want to find the length of the oil column. Say the length of the oil column is x centimeters, right? Now this you realize is 10 centimeters. So now this length is going to be 10 minus x centimeters. And at this level I can equate the pressures, this pressure and this pressure. Now the pressure at this level constituted by the glycerine column is going to be 10 into density of glycerine, which is going to be 1.3, and that's equal to x units of oil, that means x into 0.8 grams per cc plus 10 minus x into 13.6 of mercury. This is mercury, right? So x can be obtained readily from this. Fair enough? The tube is partially filled with water. Another liquid which is not miscible with water is poured in one arm. This was the water level initially. Another liquid not miscible with water is poured in one arm until it stands at a height d above the original level. So when you pour the liquid L, when you pour the liquid, not L, then it will stand at a height d above the original level. Until it stands at a height d above the original water level, but this level will dip down, it's going to dip down. The level of water in the other arm rises by L. So if the level here rises by L, the level here must have dipped by L. So this length is L and the level here rises by an amount L. You want to find the relative density of the liquid. You want to find the relative density of the liquid. Now, at this level, there is liquid column of length d plus L. There is liquid column of length d plus L. So the pressure at this point is going to be rho of the liquid into D plus L. That's the pressure at this level. Now, this is L, this is also L, so this is 2L in fact. The pressure here because of 2L units of water is going to be 2L into rho of water, Relative density is what? Density with respect to water, rho of the liquid divided by rho of water, that's going to be the relative density. So, the relative density, which is rho of the liquid divided by rho of water, that's 2L by D plus L. Clear? A balloon descends with a uniform acceleration A. The balloon. Now, what are the forces acting on the balloon? There is weight acting downwards and there is upthrust acting upwards. Under the influence of these two forces, it has an acceleration A downwards. So, W minus U would be mass of this, which would be W by G into acceleration A. Yes or no? What weight should be released so that the balloon will rise with the same acceleration? So now what I do is, from the balloon, I release a weight W1 out. So it's a discrete weight, so it's not going to affect the envelope of the balloon, so the volume will remain the same. As a result, the upthrust will remain the same, right? But the net force acting downwards would be W minus W1, where W1 is the weight released. You know what I'm saying? Upthrust will only depend on the volume of the fluid displaced. So the volume of the fluid is not changing. Fluid displaced is the same as the volume of the balloon. So upthrust will be the same, right? Now under the influence of these two forces, it has an acceleration A upwards. We then have for this situation, U minus W1 equals the mass, which is W minus W1 by G into acceleration A. Yes or no? And to be able to compute W1, you add these two, U gets eliminated and W1 can be obtained. W1 can be obtained. Add these two equations, you will obtain W1. Problem 3. There is a block of ice which is floating in water. 5 meters thick, this is 5 meters. A certain part of it is below water, a certain part is above water. Say X meters is below water. Then the weight of ice would be proportional to 5 meters, right? 5 into 0.9 grams per cc, or 0.9 is the relative. So the weight would be proportional to this. It must be proportional to the weight of the fluid displaced. Weight of the fluid displaced is going to be X into 1 for water. Of course, there is an area of cross section, but that will get cancelled from both sides. So applying laws of flotation. So then the amount that is dipped in water is 4.5 meters. This is the amount that is dipped in water. I hope all of you understand this. 4.5 meters. And therefore, this is 0.5 meters. Well, which means now if you drill a hole, if you drill a small negligible sized hole, then water would be available at this level. So you need a rope only of this length. You need a rope only of this length. That means 0.5 meters of rope is required, 50 centimeters of rope is required. Right? Which one will weigh more? An empty soft plastic bag or when it's filled with air at atmospheric pressure? Huh? Okay, how many will say plastic bag? How many would say when it's filled with air at atmospheric pressure? How many would say same? So there are so many most of you would say nothing. But I'm not giving you that option. None of these is not what I'm saying. The collapsed bag has negligible volume. Collapsed bag has negligible volume and therefore it experiences negligible upthrust, right? So its weight would be its real weight, W. Weight is going to be its real weight, right? Now you inflate the plastic bag. Now you inflate the plastic bag. Say it becomes larger, right? You fill it up with air at atmospheric pressure. You fill it up with air at atmospheric pressure. So W was the original weight and now you have W1 as the weight of the air which is with which it's filled in, right? This W1 kilograms of air is filled into the plastic bag. Good. The trade-off is that now it has a certain volume, so it has displaced a certain amount of air, so it experiences an upthrust. The upthrust would be the weight of this amount of air which is displaced, but the weight of this amount of air which is displaced is W1. So it experiences an upthrust which will also be W1. So what's the net weight? W. So they weigh the same. They weigh the same. Clear? You know what I'm saying? A stone is dropped from a boat floating in water. So this was a simple model of a boat floating in water. M was the mass of the boat and ms was the mass of the stone, right? Now, the extent of water this stone would displace when it's residing in the boat would be it would displace an amount of water whose mass would be ms. Right? The amount of water that it displaces when it's in the boat would be ms. So what's the volume of water that it initially displaces when it's residing in the boat? ms divided by rho of water is the volume of water that it has displaced by itself being in the boat. Yes or no? Isn't it? But now when you throw the stone out, then what's the volume of water that it would now displace? Its own volume. Now it's going to displace its own volume. So the volume displaced in a final scenario is ms divided by rho of the stone, right? Now obviously you would expect rho of water to be less than rho of stone. So you would expect the initial volume Vi that's displaced larger than the final volume that it's displacing. The boat by itself is displacing the same volume, but the difference in level arises because the stone residing in the boat versus rho stone thrown in the waters would displace unequal amounts of water, right? So this is the volume displaced by the stone alone. While being in the boat, stone, when it's thrown in water, this is the volume it displaces, and the initial volume displaced is more than the final volume displaced. So what would happen to the level? If it's initially displacing more water, the level would have been higher. So now the level will decrease. The level of water would decrease. Yes or no? Right? If you displace more water, the level will be higher. If you displace less water, the level will be lower. There is a sensitive balance. There is a glass bulb. There is a glass bulb which is balanced by, there is a glass bulb in one and it's balanced by a brass weight in the other one. Okay. Now one thing, if the glass bulb have the same weight, for it to have the same weight, must have a greater volume. must have had a greater volume because brass is heavier. Brass is heavier, right? So which means now the volume of air displaced here must have been much less than the volume of air displaced by this. So the upthrust on the brass weight must have been negligible compared to the upthrust on the glass bulb, right? So now when you evacuate this and you also evacuate that, there is no change in the upthrust on this because there hardly was any upthrust on this. But the upthrust on this significantly decreases. Its weight remains the same, but its upthrust now significantly decreases. Earlier, W minus U was balancing brass, right? So now if U goes away, then this will become larger than that. The apparent weight of this will be larger than the brass. So then it will go down. It will tilt towards the glass. It will tilt towards the glass bulb if you evacuate both. The loss of upthrust here is much less. The loss of upthrust here is more. So it will tilt towards the glass bulb. A body immersed in a liquid is balanced on scales. Will the reading of the scales be altered if the liquid is heated? The temperature of this rises. What would happen to the reading of the on these scales? Hey, realize that when the temperature of this rises, the density of the liquid will decrease, right? There is greater volume expansion in a liquid compared to a solid. So the change in volume of the solid would be much small compared to the change in volume of the liquid. So the density of the liquid will decrease. Now if the density of the liquid decreases and the volume of the solid does not decrease significantly, which means the weight of the liquid displaced will decrease because it's displacing the same volume but at a lower density. So the weight of the liquid displaced will be lesser now. The weight of the liquid displaced will be lesser. So the upthrust decreases. The upthrust on this decreases. Yes or no? Upthrust on this decreases. That means now the balance would be lost. The balance would be lost. So this will weigh more than this because the upthrust has decreased. So this will weigh more than this. So which means this will tilt downwards. This will tilt downwards. Does it not? I'll explain again. See, when you heat both of them, the solid and the liquid, the solid will not expand significantly. But the liquid has a greater coefficient of volume expansion gamma. It will expand more. So the volume of the solid remains practically the same, whereas the density of the liquid decreases significantly. So now it will displace the same volume of the liquid, but now it will displace a liquid of lesser density. So it will displace less weight of the liquid. So the upthrust on it will now be lesser. So the apparent weight here would now be more than the apparent weight earlier. So it will tilt downwards. That is what, right? The density of air in atmosphere, this is, let's say, sea level, varies with height as G equal to d naught e power minus alpha h. At a height h above the sea level, the density is given by d naught e power minus alpha h. If you put h equal to 0, you will get d naught, which is density at sea level. Calculate the atmospheric pressure at sea level. We want to calculate the atmospheric pressure at sea level. Now, realize that from H to H plus dH, pressure would decrease. From H to H plus dH, pressure would decrease. The change in pressure, therefore, dP would be negative. Would be negative, right? The change in pressure would be minus. Now the density over this H to H plus dH is the same as density at H. So change in pressure would be minus the density, that is rho d naught e power minus alpha h into G into change in height. the change in pressure would be negative because pressure is dpdh is negative because pressure is decreasing with height, right? Rho instead of rho, we have d naught e power minus alpha h, rho g into change in height. That's going to give me change of pressure, yes or no? All that you need to do is integrate both sides. When h is 0, pressure is P naught, which is what you want to compute, right? And when h is infinity, D becomes 0. That means, there are hardly any particles there. The pressure will become 0 at D equal to infinity. Integrate and solve for P naught. Solve for P naught. Plug in values and solve for P naught. Clear? A body when immersed in a liquid floats with 1/4 of its volume above the liquid surface. So, say V was the total volume, then V by 4 would be above the liquid surface, 3V by 4 would be below the liquid surface. Which means, let's say, if rho B be the density of this solid, then rho B into V would be like the mass of the solid. That must be equal to mass of the liquid displaced. Mass of the liquid displaced would be 3V by 4 into rho of the liquid. Yes or no? Okay. Now, when you immerse it to a depth D from the liquid surface, then the forces acting on it, what are the forces acting on it? There is weight downwards. Weight downwards means V into rho B into G. That's the weight downwards. And there is upthrust upwards. Upthrust would be because of its own volume V into rho of the liquid into G. Weight of the liquid displaced, that's the upthrust. So the net force acting would be this minus this, and that divided by mass would be the upward acceleration. So the upward acceleration A is Vg into rho L minus rho B. That's the net force upwards divided by the mass of this. The mass of this is V into rho B is the mass of this. That's the upward acceleration. And you can see from here it's G into rho L by rho B minus 1. That's the upward acceleration. Hey, but rho L by rho B is 4 by 3 as you can see. See, rho L by rho B from laws of flotation is 4 by 3. So this becomes 1/3. So this becomes like a G by 3. So it moves up with a constant acceleration G by 3. So G, the upward height traversed, is going to be half of G by 3 into T squared. T is the time taken. G then is going to be root 6D by G. That's the time it would take to reach the bubble to the surface. That's the time it will take to bubble to the. Yeah? Okay. There are 3 ingots: gold, silver and gold silver alloy. Gold, silver and gold silver alloy. Gold silver alloy. If gold loses 14 grams, so now this must also be equal to the weight. When it loses this much, that means it must have displaced this amount of water. It must have displaced this amount of water. But this amount of water, 14 grams of water, is like 14 cc of water. That means it has displaced 14 cc of water, and therefore its volume must be 14 cc. Yes or no? It will displace its own volume. When you immerse it in water, it will displace its own volume. So its own volume, which is the volume of the liquid displaced, is 14 cc. Right? Gold loses 26 grams or silver loses 26 grams. That means it has displaced 26 cc. That means its own volume must be 26 cc. And the gold silver alloy loses 18 grams. That means its own volume must be 18 cc. Right? What proportion by weight of the alloy is gold? What proportion by weight of the alloy is gold? So then, evidently, if M is the mass of gold and M1 is the mass of silver, or what you can do is, let's say if M is the total mass, if M is the total mass and then M minus M1, or M1 is the mass of gold, M1 is the mass of gold, then we just need to compute M1 by M. We just need to compute M1 by M. So, if this is the total mass, then what's the mass of silver? Mass of silver is M minus M1 is the mass of silver. And if this is the mass of silver, then what must be the volume of silver in this? What must be the volume of silver in this? By the density of silver. And what's the density of silver? 10.5 grams. So divided by the density of silver. What is the mass of gold and what's the volume of gold? M1 divided by the density of gold. That's the volume of gold. And that must be equal to 18 cc. That must be equal to 18 cc. You can now find the ratio M1 by M in this equation. Is that alright? Now 12. Now 12. जरूरत है क्या? In fact, row of silver भी नहीं चाहिए. I don't even need row of silver. I don't even need row of silver. I mean, I'll tell you what. I can replace this row S. I can replace this row S by mass by density using this data. It's the same mass for all of them, right? Say, I don't need either row of silver or row of gold. Why? Because each of these ingot is of same mass. Let's say M prime. M prime is the mass of each one of them, right? So M prime is the mass of this. M prime is the mass of this, right? So then, what's the density of gold? What's the density of gold? Density of gold is going to be M prime by 14. What's the density of silver? The density of silver is going to be M prime by 26, right? So this row S, row of silver is M prime by 26, this M prime by 26, and this row of gold is M prime by 14. And I can find M1 by M prime, M1 by M prime I can find. I don't need the density of gold or silver at all from this, right? Two identical cylindrical vessels with their bases at the same level contain a liquid of density rho. The height of the liquid in one vessel is H1, whereas the height in the other vessel is H2. The area of cross section of either base is A. What is the work done in equalizing the levels when the vessels are connected? See, there is a stopcock. When you remove the stopcock, the equalization would take place. Equalization of levels will occur. And do you realize that they will arrive at a common height H? They will arrive at a common height H, where H would be H1 plus H2 by 2. How about it? No? Because of equal areas of cross section. Essentially A1 H1 plus A2 H2 is going to be A1 into A1 plus A2 into A. And A1 and A2 are equal. So the common height is going to be H1 plus H2 by 2. Okay. Now, as far as this liquid is concerned, as far as this portion is concerned, in the initial stage, it has some potential energy. I can, to calculate its potential energy, I can replace this entire mass by a point mass at H1 by 2. Because it's a uniform G over this region. I can replace this entire mass by a point mass at H by 2 for the sake of calculating the potential energy of this unit. Yes or no? So, if A is the area of cross section, then what's the volume of this? A into H1 is the volume of this into density. That will be the mass into H1 by 2 into G. That would be the potential energy. mg into height H1 by 2. That will give me the potential energy of this. Right? That will give me the potential energy of this. That is A rho G into H1 squared by 2. That's the potential energy of this. What's the total initial potential energy therefore? A rho G by 2 into H1 squared plus H2 squared. That's the total initial potential energy. Same expression for H2, replace H1 by H2. You will get the potential energy of this. So the total initial potential energy is this expression plus the same expression replacing H1 by H2. So that's the total initial potential energy. What's the total final potential energy? A rho G by 2 into H squared plus H squared. Yes or no? H square plus H square. H square for this and H square for the same expression. That's the total final potential energy where H is this. So which is like A rho G into H1 plus H2 by 2 whole square. That's the total final potential energy. Yes or no? Now, the gravitational force is a conservative force. Work done by a conservative force is negative of the change in potential energy. So, the work done by gravity is going to be negative of UF minus UI. UF minus UI, that's going to be the work done by the gravitational force. Negative of the change in potential energy, which will turn out to be a perfect square and therefore positive. Got me? And even without saying anything, sometimes if there are just options, I would know that, well, if the two initial heights were the same, if H1 were to be equal to H2, there would be no exchange of liquid between the two containers, and therefore the change in potential energy would have been 0. So if H1 is equal to H2, then the change in work done by gravity ought to have been 0. So I know if I can look at the options, I would know that, well, for sure, H1 minus H2 must have been a factor of that. So if you look at options and if there is a factor that does not contain H1 minus, there is an expression that does not contain H1 minus H2 as a factor, you can ignore that option. Because for H1 equal to H2, the work done by gravity ought to have been 0. Got me? Two communicating cylindrical vessels, tubes contain mercury. The diameter of one vessel is 4 times the diameter of the other vessel. Means the area of cross section of one is 16 times the area of cross section of the other one, right? So the area of cross section of this is A, the area of cross section of this is 16A. And the two vessels contain mercury. A water column of length 70 centimeters is poured in the narrow vessel. How much will mercury rise in the other vessel? So now when I pour water in this of column 70 centimeters, 70 centimeters of water, this level dips by a certain amount, and this level will rise by a certain amount? Yes or no? Hey, do you realize that if this rises by an amount x, this will dip by an amount 16x, isn't it? In the narrow vessel, it will dip by an amount 16 times the wider vessel. Yes or no? So if this mercury level has risen by an amount x, then this must have dipped down by an amount 16x. 16x. Now, this is the interface between water and mercury. This is the interface between water and mercury. So at this interface, I equate pressures in the two lengths. Now, this was x, this is 16x, this is also 16x. So I have 17x units of mercury here, 17x units of mercury exerting a pressure proportional to this into 13.6, 17x into 13.6, right? That must be equal to the pressure exerted by 70 centimeters of water here, 70 centimeters of water, 70 into 1. So x can be obtained. 1, 70 divided by 17 into 13.6. These many. Two communicating cylindrical vessels, tubes contain mercury. The diameter of one vessel is 4 times the diameter of the other vessel. Means the area of cross section of one is 16 times the area of cross section of the other one, right? So the area of cross section of this is A, the area of cross section of this is 16A. And the two vessels contain mercury. A water column of length 70 centimeters is poured in the narrow vessel. How much will mercury rise in the other vessel? So now when I pour water in this of column 70 centimeters, 70 centimeters of water, this level dips by a certain amount, this level dips by a certain amount, and this level will rise by a certain amount. Yes or no? Hey, do you realize that if this rises by an amount x, this will dip by an amount 16x, isn't it? In the narrow vessel, it will dip by an amount 16 times the wider vessel. Yes or no? So if this mercury level has risen by an amount x, then this must have dipped down by an amount 16x. 16x. Now, this is the interface between water and mercury. This is the interface between water and mercury. So at this interface, I equate pressures in the two lengths. Now, this was x, this is 16x, this is also 16x. So I have 17x units of mercury here, 17x units of mercury exerting a pressure proportional to this into 13.6, 17x into 13.6, right? That must be equal to the pressure exerted by 70 centimeters of water here, 70 centimeters of water, 70 into 1. So x can be obtained. 1, 70 divided by 17 into 13.6. These many. Got it? A narrow cylindrical pipe closed at one end, contains air which is separated from outer atmosphere by a column of mercury. and the open end is uppermost. Air occupies a length x prime millimeters, with the closed end uppermost. It occupies a length x millimeters. The length of the mercury column is h. We want to find the atmospheric pressure. We want to solve for the atmospheric pressure in, say, millimeters of mercury, Okay, very simple really. Realize that the atmospheric pressure plus h millimeters of mercury is balanced by the air pressure here. Isn't it? So we have P naught plus H. P naught, which is atmospheric pressure, plus h millimeters of mercury must balance the initial air pressure. Right? So that's drawing the free body diagram of this mercury. Isn't it? So the initial pressure is P naught plus H. The initial volume of air is x prime. Now, in this case, the air pressure plus h millimeters of mercury would balance atmospheric pressure P naught. The air pressure plus h millimeters of mercury will balance atmospheric pressure. So the air pressure must be P naught minus h, right? So Pf, the final air pressure, is P naught minus h, and the final volume is x. The initial volume is x prime. So I can apply again, deploy Boyle's law to the air column. So I have P naught plus h into x prime equals P naught minus h into x, and I can very readily solve for P naught, the atmospheric pressure in millimeters of mercury. Got me? A tube open at both ends is immersed vertically in a deep vessel containing mercury, so that air in the tube occupies the length x centimeters. Deep vessel. Closed at one end. That air column is x centimeters, x centimeters or millimeters, does not matter, x centimeters. This is mercury, right? Now closing the upper end, so this was open, initially it was open. Oh, I'm sorry, open at both ends. So now closing the upper end, the tube is raised by x prime centimeters. Closing the upper end, you raise it by x prime centimeters. So now this becomes x plus x prime. Now you've seen that pipette operation, in your chem lab. How you, so you close and you pick it up. So mercury would get trapped. There would be rise of mercury in this, and it's given that the rise, okay, we need to solve for the rise of mercury in this. This is h units of rise of mercury in this final state. So the final volume of air is x plus x prime minus h is the final volume here, right? The initial pressure is atmospheric P naught. The final pressure here, realize, is, well, the pressure here plus h millimeters of mercury would be pressure here, which is the same as pressure here, which is atmospheric. So that means x plus x prime, which means pressure of air in millimeters or centimeters of mercury plus h must be equal to P naught, right? So the pressure of gas here must be P naught minus h. So then between these two states of air, I can again apply Boyle's law. So initial PV is P naught into X equals final PV, which is like P naught minus H into the final volume, which is proportional to the final length X plus X prime minus H. Get a quadratic in H and you can solve for H. You get a quadratic in H, isn't it? And you can solve for H using Sridharacharya, right? A cubical block of wood 10 centimeters along each side floats at the interface between oil and water, with its lower surface being 2 centimeters below the interface. This is oil of density 0.8. This is water of density 1.0. Heights of oil and water are 10 centimeters each. This is 10 centimeters. This is oil and this is water. We need to find the mass of the block. Very clearly, laws of flotation. Mass of the block would be the total mass of the liquid displaced. Mass of oil displaced plus mass of water displaced, right? Area of cross section is 100 square centimeters, as you can see. So then the mass of the block would be mass of oil displaced, which is 10 squared into 8 into 0.8. That's the mass of oil displaced in grams, plus mass of water displaced in grams is going to be 10 squared into 2 into 1.0. So 200 plus 640, 840. So 840 grams is the mass of the liquid displaced, which must be, from laws of flotation, mass of the block itself, must be the mass of the block itself. Find the liquid pressure at the lower surface of the cube. Find the liquid pressure, lower surface of the cube. That means liquid pressure here. Now liquid pressure here is going to be because of 10 centimeters of oil and because of 2 centimeters of water. 10 centimeters of oil, you can apply rho GH, plus 2 centimeters, again apply rho GH. That will give you the total liquid pressure. That's going to give you the total liquid pressure. So, right? Rho GH for oil for 10 centimeters and rho GH for water for H equal to 2 centimeters. That will be the total liquid pressure. A cube of wood holding 200 grams just floats in water, just floats in. This is the water surface. This is the cube of side, let's say x centimeters, x by x by x. Alright, and there is this 200 gram weight. Now, very clearly, of the total volume of water that is displaced, right? Total volume of water displaced must have been the weight displaced by this volume plus another 200 grams. So that it floats, right? The contribution to the water displaced is like 200 grams because of this. This by itself must have displaced 200 grams of water. That means it must have displaced 200 cc of water. By on its own, it must have displaced 200 cc of water. Now when you remove it, it will rise up. So it will displace 200 cc less now. It will displace 200 cc less now. That means the 2 centimeters by which it rises, must be commensurate with 200 cc, right? So the 2 centimeters that it rises, that means how much less amount of water is displaced now? 2 centimeters into x square is the volume of water which is displaced, less amount of water which is displaced. 2 into x square is the decrease in the volume of water displaced, is the decrease in volume of water displaced, which must be 200 cc. Shall I repeat? Shall I repeat this? I'll repeat. Okay. See, in this state, how much of water has it displaced? 200 grams of water has been displaced by this alone, right? That means in terms of volume, how much of water has it displaced? In terms of volume, 200 cc. So if you remove this, it will displace 200 cc less. So that rise by 2 centimeters must be commensurate with 200 cc, must be commensurate with 200 cc. That means this 200 cc must be 2 centimeters rise into area of cross section x square. That's the decrease in volume of water displayed, right? So that gives me x squared equal to 100, x equal to 10 centimeters, x equal to 10 centimeters. Clear? A glass sphere has a cavity inside it. When placed in water, it floats with 20% of its volume above the water surface. Find the volume of the cavity as a function of the total volume. Glass sphere. V is the total volume, and let's say V1 is the volume of the cavity. V1 is the volume of the cavity, V is the total volume of the envelope, right? And it's given that it's floating with 20% above the water surface. 20% above the water surface, that means 0.8 times V below the water surface and 0.2 times V above the water surface, right? We want to find the volume of the cavity as a fraction of the total volume. That means V1 by V is what we want to find, right? Apply laws of rotation. The weight of this would be weight of V minus V1. This is the weight, right? The volume that is contributing to the weight is V minus V1, and V minus V1 at the rate of 2.5 grams per cc. These many grams of this material, and this must be equal to weight of this volume of water displaced, that means 0.8 times V into 1. Clearly gives me 1 minus V1 by V is 8 by 25, which is 0.32. So V1 by V is 0.68. So 68% of the total volume is the cavity. 68% of the total volume is the cavity.